Every student of physics eventually hears the same sentence. Light is both a wave and a particle. It sounds mysterious, almost poetic, and people repeat it as if it unlocks the secret of quantum mechanics. But here's the uncomfortable truth. That statement isn't just slightly misleading. It's fundamentally wrong. Light isn't a wave. It isn't a particle. And it certainly isn't some hybrid sitting halfway between the two. If you cling to that idea, you're not learning quantum mechanics. You're memorizing a story that sounds deep but hides what's really going on. To understand why, we have to begin with the way this confusion started. In the 1700s, Isaac Newton proposed that light consisted of tiny particles, little projectiles flying through space. That picture explained why light travels in straight lines and casts sharp shadows. It fit everyday observations perfectly, but then experiments began to challenge it. In the early 1800s, Thomas Young shone light through two narrow slits and looked at the pattern formed on a screen behind them. If light were made of particles, you'd expect two bright lines, one behind each slit. Instead, he saw a series of alternating bright and dark bands. That pattern is characteristic of waves. When waves overlap, their peaks reinforce each other and their troughs cancel out, creating interference. Young's result strongly suggested that light behaves like a wave. By the mid-1800s, James Clerk Maxwell's equations reinforced that view. They showed that electric and magnetic fields could oscillate together and travel through space as waves, and those waves had exactly the speed of light. The conclusion seemed clear. Light was an electromagnetic wave. Elegant mathematics, consistent experiments, problem solved. Except it wasn't solved at all. At the start of the 20th century, physicists studying glowing objects ran into a major contradiction. Classical wave theory predicted that hot objects should emit infinite energy at very short wavelengths, a result known as the ultraviolet catastrophe. It was obviously wrong. Max Planck resolved the problem by assuming that light energy comes in discrete packets. Instead of being emitted continuously, it is released in fixed amounts proportional to frequency. This assumption made the equations match reality, but Planck himself suspected it was only a mathematical trick, not a literal feature of light. Then Einstein pushed the idea further. In the photoelectric effect, light shining on metal ejects electrons. The surprising part is that the energy of those electrons depends on the color of the light, not its brightness. Blue light can knock electrons out even when dim, while red light fails no matter how intense it is. That makes no sense if light is a continuous wave delivering energy gradually. Einstein proposed that light itself comes in discrete packets, later called photons. Each photon carries a fixed energy, and when one hits an electron, it transfers that energy in a single interaction. Suddenly, light looked particle-like again. So by the early 20th century, physicists were stuck with two incompatible pictures. Interference patterns clearly showed wave behavior. Photoelectric experiments clearly showed particle behavior. The compromise that emerged was the idea of wave-particle duality. Light, we were told, is sometimes a wave and sometimes a particle, depending on how you observe it. This explanation sounds clever, but it doesn't actually explain anything. It simply labels the mystery instead of resolving it. A better approach is to abandon the classical categories entirely. Instead of asking whether light is a wave or a particle, we should recognize that those labels come from classical physics, a framework built for everyday objects like balls, strings, and water. Quantum mechanics revealed that nature at its smallest scales does not fit into those boxes. Light belongs to a different category altogether. In quantum theory, what we actually calculate are probability amplitudes. These are complex numbers that evolve according to precise mathematical rules. They tell us how likely different outcomes are when we perform a measurement. When multiple possibilities exist, we add their amplitudes first and only then square the result to get a probability. That single rule explains both the interference patterns associated with waves and the localized detection events associated with particles. This means that when light produces an interference pattern, it is not behaving as a classical wave. What's interfering are probability amplitudes, not physical ripples in space. And when light is detected as a single click in a sensor, it is not behaving as a classical particle either. The click is simply the outcome of a quantum measurement, a discrete event produced when an amplitude collapses to a definite result. Consider the double-slit experiment again, but now from a quantum perspective. A photon approaching the slits is described by amplitudes for different paths. One amplitude corresponds to passing through the left slit, another to the right. These amplitudes combine, and their interference determines where the photon is most likely to appear on the screen. Yet when we detect the photon, we see a single localized spot. That detection event looks particle-like, but the distribution of many such events reveals the underlying interference pattern. Neither the wave picture nor the particle picture captures this fully. The photon does not literally split into two physical waves, nor does it secretly choose one path like a classical object. The correct description is that amplitudes for different possibilities combine and influence the probabilities of outcomes. That's a quantum statement, not a classical one. This way of thinking also explains why measurements seem to change what we observe. If we place detectors at the slits to determine which path the photon takes, the amplitudes for the two possibilities no longer interfere. Each outcome becomes separate, and the interference pattern disappears. The photon did not transform from a wave into a particle. What changed was the information available in the system, and therefore the structure of the amplitudes we must calculate. The same reasoning applies to electrons, atoms, and even larger systems. Electrons are often called particles, yet they also form interference patterns when sent through a double-slit apparatus one at a time. That doesn't mean electrons are secretly waves. It means they are quantum objects governed by amplitude rules. The interference pattern arises from how probabilities combine, not from classical wave motion. This realization reveals why the language of wave-particle duality persists. Historically, physicists tried to interpret quantum results using familiar concepts. Since classical physics offered only two categories, localized particles and extended waves, quantum behavior was described as a mixture of both. That language can help beginners connect new ideas to old ones, but it eventually becomes an obstacle. It encourages people to imagine that light switches between two identities, which is not what the mathematics says. Quantum mechanics does not describe such switching. It describes a single framework in which probabilities evolve and measurements produce definite outcomes. The apparent duality arises because classical intuition lacks the vocabulary to describe this framework directly. Once you accept that, the puzzle dissolves. The confusion about waves and particles stops being a mystery and becomes a problem of language. Classical physics gave us two familiar categories, and when quantum behavior didn't fit either one, we tried to stretch those categories instead of inventing a new one. But quantum objects are simply not classical objects. They obey different rules, and those rules are expressed in terms of probability amplitudes. This shift in thinking changes how you approach experiments. Instead of picturing a photon traveling as a tiny ball or a spreading ripple, you describe its state using amplitudes assigned to different possibilities. These amplitudes evolve in time according to equations such as Schrödinger's equation, or in more advanced settings, quantum field equations. The physical predictions come not from visualizing what the object really is, but from applying the rules consistently and calculating what outcomes are most likely. This perspective also clarifies why interference appears so often in quantum experiments. Whenever there are multiple ways for something to happen, the amplitudes for those possibilities must be added before squaring them. Because amplitudes carry both magnitude and phase, their combination can reinforce or cancel, producing patterns that resemble classical interference. But again, nothing is literally waving in the classical sense. The interference happens in the mathematics that determines probabilities. When we finally perform a measurement, we obtain a single definite result. A detector clicks in one place, not several. This discreteness makes the event look particle-like, but it does not imply that the underlying entity was a classical particle traveling along a well-defined path. It simply reflects the way quantum measurements work. Outcomes are specific even when the underlying description involves a spread of possibilities. One of the most persistent misconceptions arises from the idea that observation somehow forces nature to choose between being a wave or a particle. This interpretation gives measurement an almost mystical role, as if consciousness itself influences reality. But in practice, measurement is just another physical interaction. It changes the system because information becomes correlated with the environment, altering the amplitudes we must use in our calculations. There is nothing supernatural about it. It is just quantum mechanics applied to a larger system. This same framework applies beyond light. Electrons, atoms, and even large molecules can display interference if they remain isolated enough from their surroundings. The reason we don't see such effects in everyday life is that interactions with the environment quickly destroy coherence. Once that happens, amplitudes effectively stop interfering, and classical behavior emerges. The transition from quantum to classical is therefore not about objects changing their nature. It's about the loss of delicate phase relationships that allow interference to occur. Understanding this removes the need to talk about duality at all. There is no switching back and forth between two modes of existence. There is only a single quantum description whose predictions depend on how the system evolves and how it interacts with measuring devices. The apparent wave-like or particle-like features arise from those interactions, not from a change in the object's identity. This is why I emphasize starting with amplitudes rather than analogies. Once you understand how amplitudes combine and how measurements extract outcomes, the rest follows naturally. You no longer need to imagine light deciding whether to act like a ripple or a bullet. You simply calculate the probabilities and compare them with experiment. And when you do that, the theory works with extraordinary accuracy. Quantum mechanics does not merely approximate what happens in experiments. It predicts outcomes with precision that often surpasses anything else in science. From the colors of atoms to the behavior of semiconductors and lasers, the framework based on amplitudes and probabilities consistently matches what we observe. That success is why physicists trust the theory even when its concepts feel unfamiliar. Yet, this reliability makes it even more important to use language carefully. If we describe quantum objects using classical images, we risk smuggling in assumptions that do not belong there. Words like wave and particle come with built-in expectations about how things should behave. Waves spread continuously. Particles follow definite paths. Quantum objects do neither in the classical sense, so using those terms too literally creates confusion. A more honest description is simply to say that light is described by quantum mechanics. That statement may sound less dramatic, but it is far more precise. The rules of quantum theory tell us how amplitudes evolve and how probabilities emerge when measurements occur. Everything else, the patterns, the clicks, the apparent dual behavior, follows from those rules. This viewpoint also helps avoid a common trap. When people hear that quantum objects behave differently when measured, they sometimes jump to philosophical conclusions. They imagine that reality depends on observation, or that consciousness shapes physical events. But the mathematics does not require such interpretations. Measurement is just interaction, and interaction changes the system in predictable ways. The theory remains objective, even if our descriptions of it sometimes sound strange. Another reason the wave-particle language persists is that it can be useful in limited contexts. In optics, treating light as a wave often provides good approximations for interference and diffraction. In particle detectors, thinking in terms of photons can simplify calculations of energy transfer. These approximations work because quantum mechanics reduces to classical models under certain conditions, but they are tools, not truths. They help us solve problems without capturing the full nature of what is happening. Once you see them as approximations, the need for duality disappears. Instead of saying light is sometimes this and sometimes that, we say that in some limits its behavior resembles classical waves, while in others it resembles classical particles. The underlying description remains quantum in every case. That shift in wording may seem small, but it removes a great deal of unnecessary mystery. The same principle applies to matter in general. Every particle we know, electrons, protons, atoms, is described by quantum rules. Each has amplitudes that can interfere and probabilities that determine measurement outcomes. Classical behavior emerges only when those amplitudes lose coherence through interaction with the environment. What we call the everyday world is simply the quantum world seen through the lens of enormous complexity. Recognizing this continuity helps make quantum mechanics less alien. It is not a separate domain where reality becomes magical. It is the same physics operating at all scales, with classical intuition appearing as an approximation when interactions become too numerous to track individually. The theory does not divide the universe into two kinds of behavior. It describes one set of rules that apply everywhere. At this stage, the question naturally arises: if amplitudes are the central concept, what are they physically? Are they real waves in some deeper sense, or just mathematical devices? That question has been debated for nearly a century, and there is still no consensus. But the absence of a final answer has not prevented the theory from working. That's one of the most important lessons of quantum mechanics. We don't need to settle every philosophical question in order to make precise predictions. The amplitudes may be difficult to interpret, but the rules governing them are clear. We know how to calculate them, how they evolve, and how to compare the results with experiment. And whenever we do, the agreement is remarkable. Physicists have proposed many interpretations of what these amplitudes might represent. Some think they describe real physical waves in a deeper space of possibilities. Others see them as tools that encode our knowledge about systems rather than features of reality itself. There are ideas involving many parallel worlds, hidden variables, or entirely new ways of thinking about probability. Each interpretation tries to explain what the mathematics might mean beneath the surface. What matters for physics, though, is that the predictions remain the same, regardless of interpretation. Whether you picture amplitudes as real or abstract, the experiments come out the same. That is why most working physicists focus less on metaphysical questions and more on calculation. If the method predicts outcomes accurately and consistently, it earns our trust. The deeper meaning may come later, or it may require new theories to uncover. This pragmatic attitude helps keep the subject grounded. It prevents quantum mechanics from drifting into mysticism. The theory does not tell us that consciousness creates reality or that observation magically reshapes the universe. It tells us how to compute probabilities for measurable events. When we use it correctly, it delivers answers that can be tested and verified. Seen this way, the real shift brought by quantum mechanics is not that nature is paradoxical, but that our classical categories are too narrow. We were used to thinking in terms of objects and motions, waves spreading through media, or particles tracing paths. Quantum theory replaces those pictures with relationships between possibilities. The world becomes a network of interactions described by amplitudes rather than a collection of tiny billiard balls or rippling surfaces. Once you accept that change, the strange stories about duality lose their power. Light does not need to switch identities. It never was a classical object to begin with. It is simply a quantum entity obeying quantum rules. The same is true for every particle we know. The differences we see arise from how systems interact and how measurements reveal outcomes, not from objects transforming their nature. This understanding may feel less dramatic than the usual wave-particle tale, but it is far more accurate. It removes unnecessary mystery and replaces it with a consistent framework. Instead of asking whether light is this or that, we focus on how amplitudes evolve and how experiments confirm the predictions. That approach leads to real insight rather than philosophical puzzles. So, if you take one idea from this discussion, let it be this: quantum mechanics does not ask us to choose between waves and particles. It asks us to learn a new language altogether. In that language, probabilities come from amplitudes, interference arises from their combination, and measurements produce definite outcomes. Everything else is interpretation layered on top of those rules. When you hear someone say, "Light is both a wave and a particle," remember that this is just a stepping stone, a way to ease people into unfamiliar territory. The deeper truth is simpler and more powerful. Light is a quantum object. It behaves according to quantum mechanics. And once you understand that, you stop trying to force nature into old categories and start seeing it on its own terms. That shift in perspective is the real beginning of understanding quantum physics.